So with specialists today, I'm covering 9C. So you need to just remember the technique of anti-differentiation. When you have a differential equation, we looked at the for the previous part for 9b, the first derivative will be a function of x, okay? And for 9c, what's going to happen is the right hand side is going to be a function of y. So what you need to remember is there is a rule dx over dy is 1 over dy dx. Okay, so that dy dx is coming from being equal to g of y. So we substitute here g of y. So it's going to be 1 over g of y. And what you do is you rearrange the equation to separate the variables x and y. Okay, so I think it's jumping a step here, but what you would have dx over dy is equal to 1 over g of y. Then you will have dx on the left by itself equal dy over, this is horrible, so it's dy over g of y on the right hand side. And when you anti-differentiate, that's your equation, you anti-differentiate respectively in terms of dx and dy. The left hand side is equal to x because they are inverse operations, okay? And here the right hand side is an integral, okay? When we anti-differentiate the left hand side, we're gonna have a constant, but we kind of ignore it because we can when we anti-differentiate this one, the right hand side, we can adjust it to a new constant. So we ignore the constant for now. It's just when you anti-differentiate, you get the general solution with a new constant. Once you have that rule, you anti-differentiate in terms of y. So just be mindful now, everything's going to be in terms of y. So you just have to do a mental adjustment about the rules that you know in terms of x. You will get an expression in terms of y, and you might be able to rearrange it to make y the subject. Not all the time, but most of the time you should be able to. Actually, probably at your level with this subject all the time, every situation, okay? Alright, so let's do some examples. Alright, so example 9, there's going to be 4 different functions, okay? You will have so you have a situation when you have the right hand side is it's going to be a function of y. To make sure the function is defined, you will have to narrow down the domain. This is going to be useful. When you rearrange that, you'll find out that it's actually 2y plus 1 is greater than 0. Here you want it to be positive. They kind of link together because it relates to when you anti-differentiate, there's going to be a log of e. Here under the square root it's only positive, so let's start with the first one. So you have that. What you do is you need to separate the variables. Hang on, what's it's slightly different. So yeah, you have dy over dx. So you need to regroup the separate the variables. So you can flip it around, okay? Or what I could have done here is move the dx, you divide by dx, you move it to the right, and the dy plus 1 you transpose it to the left hand side. So here they just do the reciprocal equation, then they have dx, the dy gets transposed on the other side, and you get that integral. Now if you integrate that, it's a log of e. Using a chain rule, it's a log of e of 2y plus 1. There is a coefficient in front which will make a 1 over 2 appear as a coefficient. As it is, when you anti-differentiate, always remember to put a modulus. Okay, you have your constant. Now because it says y is greater than negative 1 over 2, which is equivalent to 2y plus 1 greater than 0 strictly, we can remove the modulus here. Okay, and then you would rearrange it to make y the subject, and you have a exponential function, which is your general rule. Something to annotate here: if you separate using your index law, you have your e of 2 bracket x minus k. If you expand that, you're gonna have a factor which is exponential of negative 2k, which is that one. As it is constant, we can rename it to a different constant. The notation usually is capital A because it's a coefficient in front of e. We make it capital to differentiate from the lowercase, so it's kind of a convention. So it's a factor in front of the exponential. So we get this one. Now notice that if you take the opposite, so we had the domain that is the opposite. If you were doing to do the working out, you end up with the a function that is slightly different. So the constants will be the same, but you will end up with a sort of a similar exponential. Okay, with the it has a negative, so it's a let me see, it's a symmetry of a reflection from the x-axis. Alright, b, dy over dx is equal to e of 2y. So we'll follow the same process. We're gonna need to separate the variables. Okay, so you take the reciprocal. Don't forget, with an exponential, use your negative index from your index laws to rewrite it as still as an exponential with a negative coefficient next to the y. So when you anti-differentiate, you will have a negative 1 over 2 coefficient. Okay, you have a constant. Now when you rearrange it again, you will need to rearrange to make y the subject, so you follow the working out. That c constant is over here, so just follow the steps. Now don't forget this precondition. You need to add this, so you have a negative 2 coefficient. All right, but as you apply a log to go from here, now the idea is yeah, that's fine. That exponential, knowing from the domain, it's always positive. Okay, any exponential. So what it means is the right hand side expression has to be the same. It has to also be strictly greater than 0. So when you apply the inverse, then automatically that being greater than 0, that fits the domain of log of e, which is the inverse function. Okay, so do not forget that you have that to be positive. If that is positive, it means as you simplify, it will be x minus c being negative, meaning that x has to be less than the constant c. Okay, and that's your expression of y, so it's a log. Alright, part C. Dy over dx, you're going to do the reciprocal equation to have dx over dy, and then you separate the variables. So we have the reciprocal, we transpose the dy on the right hand side. That is the using a it's the if you anti-differentiate, that will link back to the inverse of sine. Okay, if it was a usual so it's the reciprocal, it's y over a, and a will be hang on, it will be y squared over a squared. There might be a and a squared here, can't remember exactly, but it's a general formula that you can apply for anti-differentiate that kind of sort of structure. So it's a root of y minus y squared. If it was a negative, it will be inverse of cos, and for inverse of tangent, there's no square root, it will be 1 plus y squared. Okay, so here we have that. We make y the subject. There's no restriction on the domain. I think that's it. Okay, so it's a sine of x with the what's it called? A translation to either the left or the right, depending on the sign of c. Okay, so it's in the direction of the x-axis. All right, with the last one, we do the reciprocal, so it's 1 over 1 minus y squared. We have the dy on that side. Now, do not forget, so if it was a plus, you have to think inverse tangent. Every time you deal with a polynomial, always think, well, this if you have a numerator that has multiple terms, separate the fractions. Don't forget that. It's a key rule. Separate the fractions. In that situation, the numerator is unique, so you don't have to worry about that. But the denominator is a polynomial, so you have to think partial fractions. Y minus y squared, it's a difference of two squares. So you will have two factors, 1 plus y and 1 minus y. It means you can rewrite this as a sum of two partial fractions. You won't know the numerators, the unknown capital A, capital B. You replace by specific values of y to determine the coefficients, and then you can anti-differentiate. So here you separate those two into two partial fractions. You will have, as I said, two coefficients a and b. By substituting the y by 1 and negative 1, you find that those coefficients a and b are respectively a half and a half as well. Okay, we can factorize a half outside. That is the all linear expression on the denominator, so it's a log of e. Now if you have a 1 minus y, there's a negative 1 in front, so you need to have a negative 1 coefficient as you anti-differentiate. Here it will be it's a coefficient of 1, so you leave a 1 coefficient with a half. So you have that expression plus a constant because you determine a general solution. You also know that y from the start is between negative 1 and 1. So when you anti-differentiate your hyperbola into a log of e, the modulus can be removed for both of them. That's due to the restriction of the domain for y. And those two logs can be combined. We factorize a half, you use the log rules, and I will give you this log of e of that fraction of the two linear terms. Okay, we need to do this in order to make y the subject. So here we apply exponential, which is the inverse operation of log of e. So first we multiply by 2, so we have a 2 here. We apply natural exponential on both sides, and we get that. Now to make y the subjects, we transpose the denominator. Hang on. So so a trick here they did before. Again, when you have a using your index laws, you expand that, you get a constant a, because that e of negative 2c is constant, so we're going to call it a just to simplify the notation. You could leave it like that, that should be okay, just a little bit more writing. Now we transpose the denominator on the side of the exponential, we expand the bracket, and we regroup all the y terms on one side. So here they regroup on the right hand side and factorize the y, and we make y the subject, and that gives you that exponential rational kind of expression. Okay, and that's 9c.